Okay, folks, I'm going to solve two conservation of energy problems for you and with you, and you're going to kind of take that and run with it. So we're going to practice some things that we learned and apply some math to it. So first problem is here. A ball is released from rest on a hill that is 45 meters tall. What is the speed of the ball when it reaches the bottom? And so, one thing you want to do always is draw the picture. The nice thing about using energy is that the shape of things doesn't really matter. So here's the ball, and 45 meters is going to be the starting height of the ball. And then the ball is going to be going at some speed at the bottom. And so I started with this one because the forms of energy are kind of easy, but we want to do some things first. We want to say does this problem identify the system for me, or is it up to me? And if it's up to you, you have to pick a system that results in a useful law of physics. So in other words, you have to design a system that exhibits a constant mechanical energy. So it doesn't tell me what the system is. When I look at this problem, I see an object that is changing its height above the lowest point and changing its speed. And I'm going to tailor my system around those things. So my system is going to be the ball earth system. And whenever I involve the earth, I'm involving gravitational potential energy as an option. In other words, I know that it's gravity that is going to pull the ball down to the earth, toward the earth. And so if I include the earth in my system, then I have eliminated gravity as an external force. And so I'm going to be allowed to utilize the conservation of mechanical energy. So that's kind of my first step. I draw my picture. I think about, okay, what's going to happen? For now, it's kind of simple because we have kinetic energy and we have gravity and springs. And if there's a spring in the problem, then that's great. We can involve elastic potential energy. If we have an object that's changing its height, we have the earth as part of our system. So that's where we start. I think, when you draw your picture, you can also decide what types of energy exist in different places. And so you want to map things out. The ball starts the problem in the highest position it's ever in, and so you want to identify gravitational potential energy as the thing it starts with. Now it rolls down the hill, and it essentially loses all of the gravitational potential energy that it had, and in exchange, it's now moving. And so down here, it has kinetic energy. And so when you analyze this problem, you're saying, well, really what happens is the gravitational potential energy that the ball starts with gets translated or transformed into kinetic energy. And so that's kind of the story. Gravitational potential gets converted into kinetic. So I set up this equation. The initial gravitational potential energy is equal to the final kinetic energy. So I think this tends to be a place where a lot of students get lost because they don't understand the significance of this, that they're not just arbitrarily the same. They're the same because this object starts with nothing but gravitational potential energy, and then the event happens. It goes down the hill. At the end of the event, all of this gravitational potential energy is gone, and it has been replaced with kinetic energy. If you would like to do this as sort of a different process, you could start with this full equation. And so if this helps you organize yourself better, then please use this. It's a little bit more labor intensive as far as writing, but it's really not that bad. So you go through this and you think okay, this is exhausting. What are all the types of energy, and did the ball have them at the beginning or the end? And you say, okay, ball is not moving, so that's a no on kinetic energy. Ball is sitting at a height above the lowest point in my problem, so that's a keeper. There is no spring. At the end, the ball is moving, and so it has kinetic energy. However, it is now at the lowest point in my problem. I generally want to make the lowest point in my problem 0 gravitational potential energy, so let's go with that unless I have a better reason, and then no spring. So you can always like use this as an intermediate step to figure out what types of energy something has. I may ask you to do this more visually sometimes, but I think all you need to do is identify what types of energy it has in the beginning and then do the same thing for the end. As long as you've identified a system for which the mechanical energy is constant, you can then skip to this equation. Next step would be gravitational potential energy is mass times little g times that height, and so that would be the initial height of the object. And then kinetic energy is 1/2 the mass times the speed squared. And so, you notice that I didn't give you the mass of the ball in the problem, and you'll notice that you can now divide both sides by mass and arrive at an answer. So the speed of the ball, when all is said and done, v equals the square root of 2g delta y. Now, if you take a look through your kinematics work, and if instead of doing this with energy, you thought about this in terms of kinematics, oddly enough, you would arrive at essentially the same equation. And so because mass disappeared out of this equation, kinematics actually holds true. Now, the only issue with that is in kinematics, we assumed constant acceleration. We don't make that assumption in energy. So we're kind of more free to use energy when we don't know if the acceleration is constant. And even though you could use kinematics, if you actually tried to find acceleration, it would not work out like that. So you can get this equation by energy means or kinematics means. It's just that the g wouldn't be there, and for reasons that are kind of hidden from this. Okay, anyway, the speed at the bottom is going to be the square root of 2 times 9.81 newtons per kilogram times 45 meters. And that's the square root of that. And so, to calculate that out, the speed is square root of 2 times 9.81 times 45. And so 29.7 meters per second. So that is a huge hill, and that ball is moving fast. Okay, so there we go. Next problem. We have a ball bearing is launched from a spring-loaded launcher that is 1.2 meters off the ground. If the bearing hits the ground with a speed of 6.0 meters per second, what was its speed when it left the launcher? Now, here's another nice part of energy. This is a fairly complicated problem if it were a projectiles problem, but it's not. So we're going to see if it's easier, or hopefully it's going to be easier to analyze with energy. So I'm going to draw a picture. We're going to have this be the marble launcher that's kind of like sitting on the lab bench. So this is like the lab bench table, and the ball bearing, there's like a spring in here, and then the ball bearing is sitting there. And so I'm imagining that this ball is launched like up in the air, and so it's going to follow this parabolic trajectory. And so, I've got that. I can label it and say like 1.2 meters is my situation here. And then I have like a speed of 6.0 meters per second. Okay, and so this is, a little bit more complicated, and it involves like a tricky decision. I am going to have to think of a system for which energy is conserved. And so my system is something I need to consider. So I'm going to look at the information that I have. I have the height off the ground. So, basically anytime something changes height, if I want to demonstrate conservation of energy, I'm going to choose the Earth. So I can say I'm going to have this system be the ball Earth system. And then, there's this issue of a spring-loaded launcher that is 1.2 meters off the ground. And I wanted to write that into the problem to make you think about it, because I kind of said anytime there's a spring, you're going to want to use spring potential energy and have the spring be part of the system, but I'm actually going to omit it here. One of the hints is that you're not given information about the spring. The other hint is the entirety of this problem takes place after the spring is decompressed. So basically, like, you haven't used the spring launchers, but you put the ball bearing in and you use a pen or a pencil to poke the ball down, or actually there's a lever on the side to compress the spring, and then you hit a button and the spring releases. So the spring has got some spring force, spring energy stored into it. You release it and it flings the ball out. This problem takes place after the spring has been released, because the very first thing that happens is I'm asking you about what was its speed when it left the launcher. And so I'm not going to include the spring here because it's actually not involved in the sequence of the problem. The spring shows up after things start. Okay, so now I'm going to set up my energy situation. So there's my initial equals final energy. And so the thing I want to think about, and I can label this in the question itself, is, well, according to the problem, so this obviously is off the table. It's not at the lowest height possible. So I have gravitational potential energy. But also, I'm here to find the speed that it had when it left the launcher. So it's got to have kinetic energy. And then by the time the ball gets down here, well, now it's at the lowest point in the problem, and so the only thing it has is its motion, and so it's going to have kinetic energy. So my story here is this ball starts with gravitational and kinetic, and when all is said and done, it ends with only kinetic energy. And so what you want to think about is kind of the next level of thinking here is the kinetic energy of this ball is going to increase by the exact amount that the potential energy decreased. So it is trading this potential energy to get more kinetic energy. So the equation I'm going to write is initial gravitational potential energy plus, initial kinetic energy. Let's just make that go away. Try that again. Okay, plus initial kinetic energy equals final kinetic energy. So it started with potential, gravitational potential and kinetic, and it's going to end with only kinetic energy. So I write out my expressions: gravitational potential energy, mg delta y. Initial kinetic energy will go 1/2 mv naught squared, and then final kinetic energy 1/2 mv squared. So when you know you have two different speeds in the problem, you can use two different variables like we did in kinematics. There's an m in every term of the equation. So the thing you want to be careful about is if your problem involves a spring, then you won't be able to cancel mass because there's no mass in the spring potential energy. But there is there. So I'm left with gy equals v naught squared over 2, plus v naught squared over 2 equals v squared over 2. And so I want the speed with which it left the launcher. So I'm just going to solve this all algebraically before I plug things in. I'm going to subtract g delta y from both sides, and I'm going to multiply by 2. So if I subtract gy from both sides, I get this minus g delta y. If I multiply both sides by 2, I get v naught squared equals v squared minus 2g delta y. This should look so much like a kinematics equation. It's a little bit rearranged, but it really should look like a kinematics equation to you right now, because it is. And then I'll take the square root of everything, and that will be my answer. So v squared minus 2g delta y. Okay, so I know with these problem-solving videos, I'm going to try and give you different looks at algebra, and so feel free to ask me about them. It hits the ground with a speed of 6 meters per second. So 6.0 meters per second, that gets squared, minus 2 times 9.81 newtons per kilogram, times 1.2 meters. Okay, so that all is going to go in my calculator. So square root of 6 squared minus 2 times 9.81 times 1.2. And I get an initial speed of 3.5 meters per second. Okay, so The problem I wrote worked, and that is because it completely tells the story that the object traded its gravitational potential energy for kinetic energy. And so it started with a velocity or speed of 3.5 meters per second and ended up with a speed of 6.0 meters per second. And that's that. So another long one, but you got a couple examples under your belt now for mechanical energy.